Awesome. Okay, we have our recording started. I don't have anybody else, it looks like, to add from the waiting room. So I'm going to jump in to some content here, guys. So it's great to have you with me. I've been teaching multiple classes throughout the day, so I'm a little bit strung out, like which one am I doing? Where am I going? But this is AT 181. And we're technically in week 3 of this one. And let's go ahead and see what's coming up as far as assignments, what's due. And the best way I think to do that is really to get my annotation tools over here, go over here to the calendar, and we're going to click that thing and open it up. And it will show us what's coming up when. Now my calendar is going to look a little weird because I have multiple classes that I'm doing. And I know my browser is old. Okay, so here we are. We are in the first week of February. Happy February, everybody. And this particular class, I color coded it blue. And if you look over here, let's see, this is our class AT 181. And so coming up here tomorrow, but it's not due till the end of the day, it's like 11:59, we have a few things. The syllabus contract, everybody's gone through that. You click through it. I automatically know when you have it done as soon as you do something else. You had to get through the syllabus to get any of these other modules done. Now, probably one of the biggest things, especially for some of you folks that are new, are getting that SP2 safety test, online safety test done. We have a class discussion that a lot of you guys have done already. That's about getting to know you, and a few basic electrical measurement questions that we've answered a lot of these already. But if there's something we haven't answered, we'll make sure that we do that tonight. Okay, so by using the course calendar, that's an easy way to see, what's coming up due and when. All right, I'm cruising through the chat there. All right, so you guys know what's coming up due. It's if I go to discussions, right, this is where the getting to know you one is at. Remember, we have some information here about the CDX online access. And there's a discount. All the course codes are here. You're not required to get that for this class. But if it's something that you're interested in, I definitely think you can learn more with it. And I'll show you what the activity is I put together for it. It's pretty cool. In fact, it's really powerful when it comes to the electrical section. And it was one of those things where initially I made all kinds of stuff using CDX, and then I had to scale it back because I had to say, uh-oh, timeout. This is only a 1-unit class. You don't need to kill these guys. But as you know, I'm pretty passionate about this stuff. So there's just so much cool stuff. So we'll look at that a little bit later. As far as discussions, I'm going to cruise down to the one that talks about basic electrical measurements, because this is the one that's coming up. And, definition of voltage, current, resistance. You always got me busting your chops on looking around for juice, and then a little bit of Ohm's law. So we've talked about those things. We'll be talking about them more here in just a bit. Okay. I try to build my Canvas classes so that everything you need is in the modules as well. So you don't have to go to all the tabs on the side. If you just kind of peruse through here, we've been going through week 1, week 2. We're starting to get into week 3 stuff. Technically, we are in week 3. We're running maybe just a smidge behind what I had intended. So we're still kind of finishing up this basic electrical measurement deal. But you also can see the assignments and stuff, they're all hot linked right here as well, and our presentations and everything else. So with that, I'm going to open up this presentation, and that means that I will be changing my screen share. So let me do a new screen share, and we're going to go to this guy, and then I'm going to open up this guy. Oops. Actually, I'm going to fast forward down, because you know where we left off, like we talked about the water relationship of Ohm's law, right? Voltage is your pressure, current's your flow, resistance would be a kink in the hose. I started beating you up with Ohm's law, right? And it tells us a couple of things. The biggest thing to me that I like is simplifying Ohm's law right here, where we talk about volts, amps, and ohms. And you know, for automotive stuff, most of the time we're dealing with a vehicle that's got a 12-volt battery. And so as long as the battery is not dead, if we have a consistent 12-volt battery going on, well, the next thing that Ohm's law tells us, that's really the most critical thing for us, is on this next slide. And that is, it's like a teeter-totter effect. So if we have our same 12 volts, I'm going to write him up here again. That means Ohm's law is telling us, hey, if the resistance goes up, the amperage has to go down. Likewise, though, if the resistance went down, the amperage would go up, right? So those two things work back and forth. So if your voltage stays the same, it's all about this teeter-totter between resistance and current flow. Remember, it's the current flow or the amperage that does the work in an electrical circuit. It's the resistance that's supposed to be built into the device that you're trying to operate. So if that device is a fuel injector, that's where the resistance is supposed to be. If the device is, maybe it's an electric motor or a headlight or a relay or what, that's where the resistance is supposed to be. It shouldn't be in the wires that connect to our components, right? We want our wires and our electrical connections to be very, relatively resistance free, so that our current can really do its work in the components. Okay, moving right along. Then we went into some wiring diagrams, and we talked about how they're the roadmaps to our electrical system. And I said, hey, it's all about finding the key page so you know what the symbols mean. And we finished up with some series circuit exercises. We got through those, and we just kind of stopped off right here at parallel circuits. So before I jump back into parallel, let me take a pit stop right there, and I will switch up the screen share a little bit so it's a little bit easier to read, and we'll get folks added into the class from the waiting room. Welcome, good to have you here. So last week, we spent a decent amount of time talking about series circuits, and there is some important information or important factors about series circuits. Here is one of the most critical ones for us. There is a voltage drop across each point of resistance. So for instance, this is a series circuit. I only have one component. This component happens to be what? What's this electrical symbol for here, guys? You guys tell me, what is that thing? Not everybody at once now.
Resistor?
Thank you. That is a resistor, yes. So when you see that squiggly line on a diagram, 9 times out of 10, that's what that's going to mean. Hey, there's a resistor there. So I have one resistor, it's in series. What that means is I'm going to drop my voltage, my 12 volts, I'm going to drop it across that resistor. Now, to relate this to a water circuit, think of this as like, here's our garden hose, and then, uh-oh, I ran over the hose. It's got a big kink in the hose right there, okay? And my water's coming through. Well, the water gets all caught up on this side. It's trying to flow through, but only a little bit of water gets through because of that resistance due to the kink in the hose, right? if I were to tap on a pressure gauge over here and measure the pressure, and another pressure gauge over here, what I would see is maybe over here I got 40, 50 PSI of pressure. Over here I got like, 1, 2 PSI, right? Because I've dropped my pressure across this resistance. It just, when I try to flow stuff through there, I can't flow it through and maintain the pressure. And that's how it works in an electrical circuit. Whenever current flows through a resistance, it's going to have a voltage drop. So think of that voltage drop, it's a pressure drop, right? So there's a voltage drop across each point of resistance. That also means that if I measure a voltage drop, or VD, for voltage drop, that's another way to say, oh, there's some resistance there. So VD does not equal, in our perspective, it does not equal like venereal disease. It means voltage drop. And what that really means for us is, hey, there's some resistance there. Okay. So remember I said earlier, if the circuit is built correctly, I should not have any voltage drop or any resistance in the wire leading up to my component, or on the ground side going away from that component, right? My circuit should be designed so that I drop my voltage. I should have my resistance located in the component I'm trying to operate. That component in that picture, that could be a rear window defroster, because it's basically a big resistor grid. As the current flows through it, it gets hot, and that's what takes that fog off of your rear window. And if you've ever turned on your rear window defogger, you'll notice that it bogs down your car quite a bit, because it does take quite a bit of current through that big resistive element on your back window to make heat and defog that rear window. So in a lot of cars, they might have, if it's a luxury car, it's likely to have heating elements in the side mirrors and all kinds of stuff. If you turn all those suckers on, that's a pretty big electrical load on that vehicle, and you'll feel the engine maybe run a little different when that happens. Okay, well, as the current flows through the resistance, it makes heat, and that's what causes the windows to defrost. Well, this could be the basic schematic of that. I got one defroster grid. It's in series all by itself. That's it. Okay. It's going to drop the voltage over the element, and it shouldn't be dropping the voltage across the wires or the connections leading up to it or the connections going to ground. I should drop that voltage across the component. What that also means is that each point of resistance takes its share of the source voltage. So in this case here, I have two resistances in series. That means they gotta play nice. They gotta be sharesies. If I have 12 volts total, maybe he's gonna drop, I don't know, 8 volts, and the other guy is gonna get the other 4 volts. Whatever it is, whether it's 8 and 4 or 6 and 6 or 2 and 10, they have to add up to 12 volts. They can't be more than the source voltage, and they can't be less. And if you think about it in a water circuit example, let's say the water flows out of this hose and then it puddles on the ground. Well, if the water is puddled on the ground, at this point, it has no more pressure at all, right? So whenever I'm at the end of my electrical circuit, all the voltage has to be used up at that point. Okay, I had to have dropped all that voltage. And that's why we say, hey, the sum of the voltage drops have to equal the source voltage. Okay, I can't have any voltage hanging around or just not being used. I got to end up where I've used it all up by the end of the circuit. Okay, so some of the voltage drops are going to equal the source voltage. That's Kirchhoff's law right here. And he also has a current law that we're going to look at in a minute, because it's really about parallel circuits. Okay, so hang on to that. So we went through And I think we did answer a few of these circuits, but we didn't do like this first one. So tonight, what we'll do is I'm going to do this very first circuit here. I got to get my zoom controls out of the way. They're messing me up. We're going to do this one. And why? Because this one's kind of interesting, the way it's drawn some stuff, and there's real different ways to measure stuff. And so it wants to know, hey, what's the total resistance? How many amps are flowing through this circuit? Okay, we can do that. And then it wants to know the volts at the different spots, okay? And that will line up with what we were just talking about. All right, so for this, let me sit down here and we're gonna get this thing figured out. Okay, so get my annotation tools on there. So let's start with the two things over here. How do I figure out the total resistance, RT? I don't know why they don't say TR, but it's always RT. So what's my total resistance or resistance total? Well, it's the sum of the individual resistances. Whenever you have these like problems, these kind of math Ohm's law problems, you don't factor anything in for the wire. So you go, okay, well, I got 2 ohms here, plus another 2 ohms here, plus another 2 ohms there. So 2 plus 2 plus 2. Oh, well, I have 6 ohms total. Boom, that's easy, right? Well, what about the amps? That means I better break out my Ohm's law pie chart over here. There he is. Volts, amps, ohms. And I know the volts and I know the ohms, but I want to know the amps, right? So, well, that says if I cover this one up, that says, okay, the volts divided by the ohms is going to equal the amps. So 12 volts divided by the 6 ohms. Oh, okay, 12 divided by 6, that's 2. So we have 2 amps flowing through the circuit. So I'll make sure I label that. So remember, the rules to a series circuit always play in to that circuit, right? So one of the series circuit rules is that the current flow is always the same throughout the circuit. And if you remember, that current flow is the flow of electrons, right? So if I have 2 amps worth of little electrons here flowing out of the battery, they got to still be flowing here. They got to be flowing over here to ground, those little electrons, and they got to be flowing all the way back to the other side of the battery, right? So that makes sense that the current flow is going to be the same because there's only one path for the current to flow. So I got 2 amps in that circuit. Well, then where this particular one gets a little weird is it's saying, hey, I want to know the volts at these different spots. Okay. So here's what I'm going to do. In those boxes, I'm going to draw on our handy dandy voltmeter here. So this voltmeter I have is green. I'm going to make this thing green then. So here's my voltmeter here. Then I plug it in right there. Then I plug it in right there. And how am I hooking it up? Well, what I'm doing is I'm going to take the positive lead and I'm going to go right here. Right there and right there. And I'll take the negative lead and it's like I'm going to ground. Negative lead is going to ground, going to ground. So it's kind of like I took my meter and I measured it in 3 different spots. The negative lead or the COM lead stayed on ground, right? Maybe the frame of the car, maybe the negative post of the battery. It stayed there. The positive lead, first I had it before this first resistor, then I had it in between those two, and then I had it in between those two, right? And oops, I didn't draw this one over here, but there's one over there. So how would this work? Well, if I wanted to mathematically calculate it, I could figure this out. Why? Because the voltage, that's Ohm's law tells us what to do. if I want to know the volts, oh, that's the amps times the ohms. All I got to do is multiply those two together. So in this case, then, what I would have is I would say, okay, well, I have 2 ohms. Well, I'll say I have 2 amps, and I'm going to multiply that by, if I can get that, I'm going to multiply that by 2 ohms. And of course, 2 times 2 is, not dollar sign, is 4. Well, each one of these suckers is the same, right? So what that means is that this guy would drop 4 volts across him. This guy would drop 4 volts across him. And this guy would drop 4 volts across him. But you can see there's different ways that you can hook up your meter. In fact, I'm going to draw another meter, but this one, I'm going to, basically, I'm going to connect him a little differently. So here's my meter. Okay. And now I'm going to take the positive lead and I'm going to go right there, just like the other one is, right? Basically hooked to the same spot. I'm going to take the negative lead now, though, and I'm going right behind that guy. So I'm going across that component. Okay. And what this means is, based on this math, is that this resistor is going to drop 4 volts. So hooked up between here and here, what I would see is a multimeter that read, put it in there, it would read 4 volts. It'd have a voltage drop of 4 volts. That also means that this guy is going to drop 4 volts, and this guy's going to drop 4 volts, right? And of course, 4 plus 4 plus 4 equal 12. So that makes sense. The sum of the voltage drops equals source voltage. Well, how's it going to look on the meters that are drawn up in the top row? Well, they look a little bit differently, don't they? Because we've connected the meters in kind of a different format there. So how would it be? Well, you guys tell me, what would this first meter say on it? What do you guys think?
Give me 10 volts.
Okay.
Oh, no, it's give me 6 volts.
All right, I got a couple votes here for 10 volts and 6 volts. Those are good tries. It's not, though. It's 12 volts. Okay, so here's how I go. You start off with 12. I dropped 4 across this dude. So now 12 minus 4 is going to be what, 8? So this meter now would say 8 volts. And this meter now would say 4 volts. And this one that I kind of forgot to label just right, but this one at the end, he should say 0 volts. Okay. And so why I'm pointing this out is sometimes I'll see a student hook up their meter one way, or they'll hook up the meter the other way. And sometimes I've even done it. And I think, wait, that doesn't make any sense. And it's like, oh yeah, it does, dummy. Like, you're not thinking about it right. Look at how you've hooked up your meter. So are you measuring your voltage drop across a component, or are you measuring your voltage drop across multiple components, or multiple parts of the circuit? So if I think about this first meter, why does he say 12 volts? Because essentially he's measuring the difference in electrical pressure from this point that's going almost really close to the positive battery terminal, let's say. And then he's measuring that pressure difference between there and all the way to like the negative side to the end of this thing. So he's measuring the voltage drop across all this stuff. Better clear some of this stuff out of here. This next meter, well, he's measuring the voltage drop from this point and then across all this stuff, okay? Because he's hooked between there and ground, right? And so you can see that's why the meters kind of steps down in different segments. So it really depends on where you put in your meter leads. Both ways make sense when you think it through, it is easy when you're like underneath a dash or all in a weird position on a car, or it's late in the workday or whatever. And, you know, sometimes we're trying to diagnose a car and the shop's really noisy. You got, you know, I don't know, ham-fisted Joe next to you, like impacting 100 things apart. And, you know, it's hard to think sometimes in the shop because it gets loud and stuff. I mean, back when I was, you know, a real tech doing diagnostics, there was times where I had cars that were difficult to diagnose, and I'd be like, I can't do it right now. And I would go in on the weekend when the shop was quiet and other people weren't there, and I'd figure that stuff out. And I kind of had that agreement with my shop owner for certain times. There was some times where I'd leave early, and like, you know, when I first started teaching, I'd leave early a couple nights a week so I could get to my class on time and start get prepped and ready to teach. And so how I made up for that is I would come in on weekends and stuff, and I could get more done in a few hours of quiet on a weekend than I could, you know, sometimes all day, it seemed like. So it's difficult in a shop environment. And so, you know, things matter. Like, how did I set up my meter leads? You know, does that make sense? Both ways make sense when you think it through. Okay. So we just figured out the math on this. Remember that the whole reason we figure out the math is the idea of I walk over with my meter, whatever that meter is, I'm going to test the car. If I have it straight in my head of what I should be measuring at this point, and I don't measure what I think, I thought it through correctly, then I've just found my problem, right? All right. I'm going to mute a couple guys because I'm getting a little bit of feedback through there. So make sure you click the unmute button if you have a question or a comment. You can also put stuff in the chat. So hopefully that made sense to you. What we're going to do, of course, is put this on YouTube. I have some of my last semester's classes up now, and I have this, I'll get this semester's up. I think I have last week's up. But we'll get these classes posted. So if you're still having a hard time with this, you can watch it again and use some of those other supplemental materials, and hopefully it'll start making sense to you. Sometimes it doesn't make a whole lot of sense until you start testing stuff. So it might be like, this doesn't make sense to you until you start measuring stuff with your meter, and then you come back and you watch this thing again. Okay. All right. Well, I'll be honest with you, the series part's the easy part, guys, because when stuff gets parallel, that's when it's getting real. Parallel circuits are used all over the place on our vehicles. And the reason is, hey, there's more than one path the current to flow. So like if resistor 1 here took a dirt nap, right? If that failed, well, guess what? Resistor 2, he'd keep on working. And that's why we like to use those, right? So if one of your headlights, if the bulb goes out, the other one stays working. And so that makes sense for a lot of circuits in our vehicles and in our lives in general, right? But what makes it so practical and useful to us is also what makes it more complicated for our brains to figure out, because now, same thing, we have more than one path for current to flow. So, you know, this side can keep working almost independently of what's going on with this side. That means that each device receives full source voltage. It has its own path to ground. And here is the kicker. This is the real brain teaser part. Total circuit resistance is less than the lowest resistive branch. That's huge. And that's what usually, you know, blows up everybody's heads. In that, let me give you an example. We know we have 12 volts here. Let's say that this is 6 ohms. This one's also 6 ohms. Okay. The total resistance of this circuit, the RT, it wouldn't be 6 ohms. It wouldn't be 12 ohms. It's going to be less than 6 ohms is what this is telling us. In fact, I'll tell you what it's going to be. It's going to be 3 ohms. And the best analogy that I have come up with, guys, is it's like adding another lane on the highway, right? You went from one lane and maybe traffic's backed up and everybody's going 35 miles an hour, right? Maybe you add another lane on, and another lane, you know, it's a carpool lane, so not everybody gets to use it. So the lane that everybody gets to use is still kind of trafficy, and maybe people are going 40, 45, and in the carpool lane, people are going, I don't know, 50 or 60. I'm still overall flowing more cars, right? So every time I add a lane, I can flow more cars. There's less resistance to the traffic flow, right? That's what we're getting to here. Every time I add a branch, it's like adding another lane on the freeway. And now I should be able to flow more cars, right? So because current, right, the flow of electrons, some of them can go through that branch, some of them can go through that branch. Because they have more than one path here, essentially I've cut my total resistance in half. And there's different ways to figure that out. What I did is I did like the cheater method, okay? And somebody was asking me about this in one of my other classes, and I didn't actually type it out really good. So I'll make sure I put it right here. The cheater or fast track method, you know what? This is automotive. We're going to say the flat rate total resistance method. If all the resistance values are the same, it only works with same resistance values. You take one branch and divide by, so divide by the number of branches. So in this case, what does that mean? Well, I had two branches, they were both 6 ohms. So what I could do then is I could take this thing set up here. I could take one branch, which has a value of 6 ohms, divide that by 2, because there's 2 branches. Oh, that equals 3 ohms, right? Now this could work for multiple branches. Let's say I had 3 branches of 6 ohms. So I'm going to add another branch here. Ugly looking resistor, but he's also 6 ohms. Well, now I have 6 ohms divided by 3 branches. Now my total resistance would only be 2 ohms. Okay, so that's how that works. When they're the same, it's really easy to figure them out. Okay, that's your kind of fast track total resistance figuring stuff out method. All right. So total circuit resistance less than the lowest resistive branch. Can't stress that enough. So we got it here in some bullet points. A couple other things of note on this particular screen. How about this one right here? If the resistances are different, the current flow in each one of the branches is going to be different. Okay. If they're the same, of course, the current flow should be the same. And here was the thing that I just went over where I kind of did the quickie flat rate method to figuring it out. Okay, moving right along. So resistance in each branch determines the current. Current's lowest in the ones with the highest resistances, right? That's just Ohm's law. Of course, each one's receiving full source voltage so the voltage drops across each load are the same. So no longer do the sum of the voltage drops equal source voltage because we're not doing series anymore. This is a parallel deal. So it's a different set of rules here. Okay. Moving right along. So a couple different pictures of some parallel circuits. And of course I could turn the switch on and off for one, and the other one's going to keep working, right? Now I'm going to skip over this method. I don't know. The last couple times I've been trying to show people this especially on Zoom, it seems like they get all messed up. Here's what I will say. is that we have different tools in our toolbox, right? Like maybe on a job, I need a Phillips screwdriver like this, right? Maybe another job, I need a pry bar. Another job, you know, an impact gun works really well. I don't necessarily need every tool for every job, right? And there's sometimes where I could use some hand wrenches and get the job done. And there's other times where that impact gun is going to make the job a lot faster, right? These methods to figuring out these problems, whether it's product over sum, reciprocal, total current, and it's one of those things like they're just different tools in your diagnostic toolbox to figure out these problems. They can all get the job done. Some are faster than others. Some are easier to understand than others. Okay. So here's what we'll do. We'll start with the product over sum. I'm going to skip this reciprocal one. This is one that's, you can do problems quickly. It tends to blow up everybody's heads. So if we have time at the end, we'll get into it, okay? And we're going to then focus on total current, and I'll show you why that's kind of like my preferred method, okay? So with that, let's keep going. Get this thing running. Okay, product over sum. If you have two branches at a time, so here's the thing. You can only do this thing when you're working with two at a time. Once you get more than two, you can only do two at a time. So you got to do like two and then kind of move your numbers down to the next two. It gets pretty clunky doing more than two at a time, right? It's like, you know, it's a ratchet and I can get the job done with the ratchet, but you know, the air tool is going to be faster, right? But you know, it's pretty simple to do this because all you do is you figure out the product and you figure out the sum and you divide them out. So again, I'll use the same numbers that I had before, guys, where I had 6 ohms there and I had 6 ohms over there, right? So here's what I would do is I would say, okay, well, I got 6 ohms times another 6 ohms. All right, well, what's that going to equal? Oh, that's going to equal 36. Well, this mess of stuff is over 6 ohms plus another 6 ohms. All right, well, what does that equal? Well, that equals 12. Oh, well, what's 36 divided by 12, right? How many times can 12 fit into 36? Well, it can go in there 3 times, right? So if I do all this, yeah, my answer is 3 ohms. And of course, what are we figuring out? Well, 3 ohms is our total resistance, right? So the product over sum method does work. And it'll even work if I have 2 resistors that are different values, okay? So let's say I have, let's change these up. Let's get rid of some of this stuff. Let's say now, okay, this one has a value of 10 ohms. Okay. This one has a value of, I don't know, 20 ohms. Okay, well, this thing will still work, right? 10 ohms times 20 ohms, right? Oh, well, that's going to equal 200. But 10 plus 20, well, that's going to equal 30. Now I end up in a weird deal where I'm trying to get 30 into 200, right? So if I divided that out, right? In fact, I'll do it. This is one of the things I wanted to do. Let's see. We will change the screen share. I'm going to do a few housekeeping things. There we go. I'm going to change the screen share. And now I got my whole screen sharing, and you can see I got my calculator up here. So I got 200 and I divided that by 30. What's my total resistance now? Oh, well, it's 6.66, meaning that the total resistance of that circuit, even though, let me write some of this stuff down here. I'll get my pen going, change the color. So my answer is 6.66, right? We'll put 6.7. I don't like having 3 6s on there. 6.67 ohms. All right. And I better label that. So I said I had 10 ohms here and I had 20 ohms there. Well, remember, one of the rules is that the total resistance had to be less than the smallest branch, the least resistive branch. Well, I know my answer has to be less than 10 ohms, right? Well, is 6.67 less than 10? You bet it is. So that works out, right? So product over sum, the two sides don't have to be the same, but I can only handle 2 at a time, right? So it's limited, but it's a pretty easy formula to figure out, right? Okay. So hopefully that's sitting okay with you guys. I am going to just kind of cleaning up my desktop here. So with that, I can get this thing moved. All right. Oops. So now we're going to jump into this total current method. I think. Yep. Hang on. Sorry. I really want that calculator back up there. There we go. And of course, I lost the calculator, but okay. So with this method, what we're going to do is we essentially figure out how many amps are flowing through each branch. And this is kind of like the slow method. This is not the flat rate method, but this is like the guy working at a classic car shop that wants to do everything perfect, okay? This is the concourse, Jay Leno mechanic, where it's got to be just picture perfect. So it's slower, but you figure everything out, okay? That's what I like about this one. Okay, so there's not necessarily an equation other than Ohm's law. So I'm going to put my Ohm's law pie chart along the side here. Volts, amps, ohms. And essentially what I'm doing is I'm going to figure out how many amps are moving through that branch, how many amps are then moving through that one, how many amps are moving through that one, and all 3 of those get put back together, right? And go into the battery and go out of the battery, because Kirchhoff's rule of parallel circuits, his parallel circuit rule said, hey, if I figure out how many amps are flowing through each branch, that one, this one, there could be 5 branches, 10 branches, 100 branches. If I figure out how many amps are flowing back through each one of these branches, they all have to come back together at some point to go into the battery. That's going to equal my total current leaving the battery. Once I figure out my total current flow, I can then use Ohm's law to figure out the total resistance, because the volts divided by the amps equal the ohms. In this case, it'd be the total amount of ohms, right? So that's exactly what we're going to do for this circuit. And so, like I said, it's a little slower, but you figure everything out. So for instance, this has a resistance value of 4 ohms, right? Why? Because it told us it, 4 ohms. So it also tells us, hey, I have a voltage value of 12 volts from that battery. Well, Ohm's law says, all right, well, I have 12 volts divided by 4 ohms. So 12 divided by 4, that's going to equal 3, right? So I have 3 amps moving through that branch. What's the next one? Oh, it's 6. So I have 12 volts divided by 6 ohms. Oh, okay. I got 2 amps moving through that one. Okay. Well, what about this one? This one isn't quite so clean. I got 8 ohms there. Well, I have 12 volts divided by 8. Let's see, 8 goes into the one time. Then I got a remainder of 4. So this is 1.5 ohms. My ohm symbol did not come out very good there. All right, so what that means is what's my total amount of current flow, total current, or my total amount of amps leaving the battery and going back in on the other side. I just got to add these three things together. So the 3 amps plus the 2 amps, oh, that's 5 amps. The 5 amps plus another 1.5 amps, oh, that's going to be 6.5. So my total amount of current flowing in this particular circuit happens to be 6.5 amps. Okay. And all I really had to do was use Ohm's law and know my parallel circuit rules to figure that out, right? So hopefully that we're doing good so far with that. So now the next thing that happens here is that I need to I'm going to clear this out, because now what does Ohm's law tell us? Well, Ohm's law says, hey, if I know my voltage and I know my current flow, I can figure out my resistance. All I got to do is I got to take that 12 volts. So let me type it into the calculator. I got my 12 volts. I'm going to divide that by my 6.5 amps, 6.5, and I end up with 1.85 amps or so. I'm sorry, 1.85 ohms. So I will write that down. 1.85, and this is ohms. Now, is that less than the least resistive branch? Yes, it is. My smallest branch is 4. I'm less than 4. I'm 1.85. So it logically makes sense with the way that these circuits work. And if I hit the button, we should be able to check our work here. Boom. And we got it. Okay. So figuring stuff out on a parallel circuit's a little different. Total current method, though, for me makes the most amount of sense. And when I've done that, I not only know what my total resistance is, I know how many amps are flowing through every part of the circuit. And so I know a lot of information, and it gets me thinking about how the circuit works. And that's what I like about it. So it's not super fast, but it does get you thinking about how the circuit works. Okay. So moving right along. There's really only 2 types of circuits out there. There's series circuits and parallel circuits, but you know what we do? We squish them together for a series parallel circuit, and we do this all over the place. In fact, on our cars, we oftentimes will have a series parallel circuit. The series part is the control. So I'm making this a variable resistor, and I'm going to turn these not from resistors. These are becoming some light bulbs. In fact, I might add another branch here. I'll add another light bulb. And my example here, if I do this, is, let's say it's your dash lights, right? There's backlit, all the buttons on your dash, the gauges, you know, where the heating controls and stuff are. At night, all those have nice little backlights so you can see what the controls are when you're driving down the road, right? But you might want that backlighting to be real bright. You might want it to be kind of dim, you know, and so you have a dimmer switch built into the car somewhere that you can slide this guy back and forth, and it will change the brightness level of all those lights, right? And the way these lights are wired up is the lights themselves are in parallel. So if one of these guys burns out, right, well, the other ones keep working. It's just that one spot's dark at night, right? And I can have another one fail, but the other guys will keep working because they're in parallel. The thing is, if the dimmer switch burned out, they would all go out, right? Because that part's in series. And that's an important thing to understand. So if everything goes out at once, I'm looking for what's in series part of the circuit, right? And that's important to understand. It can, it would save me a lot of time than me checking all these other lights individually. If they all went out at once, I got to go with what's on the series side of that circuit. What else in a common car electrical system, what else are we typically going to put in series with the circuit? You guys tell me. What else am I going to put in here, guys?
Fuse.
Yeah, exactly. My circuit protection device, my fuse. So I would wire in my fuse like right here, so that, let's say this guy had a short to ground and he wants to pull a zillion amps, it's going to blow that fuse. Okay. So your controls and your circuit protection devices will usually be in series. A lot of the components will then be in parallel. It's really only for like sensor circuits and some very unique situations where you have like multiple things in series with each other. Okay. Mostly components will be in parallel, and controls will be in series. All right. So how do you figure out these suckers? Because you got twice as much stuff going on now. Like what's my method? What's my angle of attack? Well, what I want to do is I want to figure out what's going on with the parallel half first. So if I'm going to chunk this thing into halves, I'm going to figure out the parallel part first. And what I'm actually going to do is I'm going to then figure out his equivalent resistance, and then I'll treat it as a big series circuit. That's my method to figure those suckers out. All right. So that's pretty good there. What I want to do though, because I promised you guys I'd do some other stuff, and so we need to shift gears a little bit here. And what we're going to do is I'm going to change my screen share. Share. I'm going to go back to our course. And there we go. That. Okay. So I'm moved back to our course, and I said, I would show you some stuff here related to CDX and the safety test. Remember, if you Google search CDX fundamentals of automotive technology or the CDX FAT, it'll take you to the website. I think I've demoed that stuff before. What we're jumping into is the A6 electrical area. And I just want to show you some of the stuff that's in there real quick in our last kind of few minutes for tonight for 181 material. Let me make my screen a little bit bigger. And so there's lots of good stuff in here. I'm going to click this meter circuit one. So anywhere where it looks like a little book, if you click that, that's kind of like the textbook information. And so you have your textbook, like written text here, but then they're going to put in, of course, pictures. But if you scroll down, there's also built-in video clips.
There are two major types of voltmeters. These are...
Okay. So when you go in the book mode, they're kind of like embedded in there. And if you go, it's got all kinds of figures and that type of stuff. So that's one way, excuse me, to use this. If I go back on this thing, if I click my back key here, try it again. And I go all the way down here to my media gallery. I like this because I can skip to exactly what I want to do. And what I like about this thing is it's got all these animations. And these things are actually pretty good. So I'm going to click one. I've probably opened it up 50 times now because I clicked it so many times. Yep, of course. But what's cool about this is they have this little fluke meter, and I can interactively do some stuff. So it's a way that you could test stuff with a kind of faux meter, and you don't have to worry about blowing up your meter. Okay. So first I'm going to put my leads in there. I'm going to put that guy in the COM port. Put that guy in that port. I want to measure some voltages. So I'm going to go to volts, DC. And now I can put my lead in there. And I can put my lead over here. And I can measure that voltage. I can turn my switch on. And so you can see I got two lights here in series. One's brighter than the other. But I can measure my voltage at different points in the circuit. And go, oh, well, that bulb at the end's the one dropping all the voltage. Okay. So this is pretty cool. Now, I think I said this to you guys last week, but I'll say it again tonight. For right now with our meters, we're going to stay out of this amps position right here. Old, I shouldn't say old. Shh, don't tell her I said that. Mrs. Toshima, Miss Cheryl, she would say, stay out of the A-hole here. That's what I want you to do. Stay out of there, because watch what would happen if I went over there and I just started messing around here with my meter and I wasn't really paying attention to what I was doing. Get on there. And I hooked it up wrong. Boom. I just blew up my meter. Okay. Really what would happen is you blow the fuse on the inside, but you get the idea. So, this is a safe way to test things out. There's all kinds of stuff that you can do with your multimeter on this thing. And then there's wiring diagrams and there's all kinds of cool stuff. So if I close out some of these, 50 windows I opened up, and I go back to our Canvas page, and I scroll down here. It's quite a ways in here, but I have something called, where is it? CDX Pro Work. And this is something that you might be interested in doing if you've chosen to get the CDX, and I got the course IDs and all that stuff. But basically, I'm asking you to cherry pick a few things out of this CDX and fill stuff out, and you take some screenshots. And we're really still kind of just scratching the surface of what's in here, but it's definitely pretty cool. They trace the wiring diagrams exactly how I would trace it with pens and paper. It's pretty neat. So, and then there's some of the multimeter stuff that I was having you just kind of demoing. They're testing a Hall effect sensor. So anyways, it's one of those things where if you were gonna really get into cars, I say CDX Pro, like if you were gonna be a professional, but I would go as far as to say, like, if you just are gonna be like a really involved hobbyist, you will learn more from what we're doing if you have access to this. And so I just wanted to scratch the surface and click on a few of those demos. Now, as always, I always like to end on a tech tip. And so my tech tip for you guys for this 181 group, if I change my screen share yet again, and I minimize this and I turn back on my document camera, which auto turned off on me, is to always go back to our meters. And of course, I got all kinds of things up at my desktop here, but so here I have my multimeter. We have some of these meters at the campus, and I am still getting it worked out, but like we can check some of these meters out to you guys. So if you're strapped for cash and you're like, man, I don't have $20 to buy a meter or what, you know, you can check one out from the school. The first thing you guys need to do then is come see me, or I'm sorry, not come see me. You can't come see me. Send me an email. Send me an email and let me know, hey, I would like to check out one of these meters. And I will send you the links and stuff to do that. There's a little spot on campus where students are going to pick things up and kind of check things out and return things. So anyways, last week I did some demos with this, right? We tested our body's resistance, and then we tested the resistance on a piece of paper here, and we saw that based on how close together or far apart we were, that the resistance here changed. And I asked you guys, well, what kind of sensor would this be on the car? And I asked you to think about that. Does anybody remember? Does this seem familiar at all? Going back and forth and going back and forth. What is this thing, guys? This kind of relates to my other class as well. This is essentially like a resistor, right? But its resistance value changes with its position. Of course, now I'm getting, there we go. Now I'm getting some resistance. And so, you know what happened is I went back and forth. It was working, and then all of a sudden, it's not working. This is an example of a variable resistor. So I'll draw the schematic symbol for it. Here is a resistor. And if it has a little arrow line like it, that's a variable resistor. This one would vary its resistance with position. Okay, so that's a potentiometer. In fact, on the car, this would be a 3-wire, typically a 3-wire sensor. So you have a signal, a ground, and here would be my signal wire. And so it changes its resistance with position. And just like my piece of paper here, as I went back and forth a bunch of times, eventually wore out. Guess what? These guys eventually wear out themselves. So the old ones that had a little wiper arm moving across a piece of resistor wire in there would wear out just like my paper did. And of course, they wear out where they're rubbing along the most. So usually if it's a throttle position sensor, that's somewhere around, you know, like a quarter throttle, third throttle. So if you had a car that was fuel injected and it had a throttle position sensor like this, and it has a hesitation on acceleration, I'm going after that TPS. Okay, so that's a good example of an old school non-Hall effect throttle position sensor, or TPS. So that's your little tech tip for tonight on your meters. I think unless you've taken other electrical classes, for right now, we're just staying in these two leads. You guys can measure voltages of stuff. You can measure resistances. We'll be getting to current measurements next week. Okay. So hopefully that makes sense. Does anybody have any questions out there as I switch this thing back? Any questions? Let me see what's in the chat. Okay. All right. So I don't see anything jumping up out there at me. All right, guys. Well, thank you for being with me tonight and putting up with some of that electrical information. We'll keep going on. So next week we will completely finish up that presentation on basic electrical, and we're going to jump into really using the meter hardcore. And I have multiple multimeter demos to do. In fact, next week for our electrical class, the 181 class, we'll be using the full time. I won't be doing a split class again. So we'll run it on Com4 Zoom, and we'll probably be spending like a good hour and a half going through a bunch of stuff. Okay. Let me check the chat one last time. Okay. So that's my signal. If you guys are in both classes, that, you know, take a quick break. If you need a quick break, I'm going to stop one recording and start the other. So thank you guys. If you're only with me for 181, thank you for being here. I'll see you next week. Make sure you email me questions and stuff. Let me know if you need a meter. All right.
Bye, Mr. French.
All right. Bye, guys. Bye. All right. We'll stop that recording.